Many of you were interested in joining the lab as volunteers or as DRAs. Some of you are auditing the class and would like to have access to the Material 3 class. The answer is yes to all. I just haven't had the physical time to get down in the system and do those things. So I have not forgotten. If it is still more than a week that I have not replied to you, please send me a reminder. Everything is in my email. The problem is my email is growing enormously. So we had a visitor on Tuesday, a very important visitor from Germany. Today we will have, in any minute he's going to walk in, the president of the American Welding Society. That's a very big deal. Hey, and having a charger is even bigger deal. This is awesome. Thank you, Louis. Let's see. Yeah. So this is fantastic. Let's see if it gets there. Yeah, guys, you're in so super good hands with CCMAC 2. Let's see. Okay. So I think yes. Thank you, Louis, saving the day. And another guy of the guys in the lab is loaning this, so probably this guy will be. His computer will be without battery now. But you have the class, he doesn't have his research. Now we're good. So we're going to have the visit of the president of American Welding Society. This year is the centennial year of the American Welding Society. So it was in 1919, right after World War I. And when it played a significant role welding some things, but it was very rudimentary. It was a very major player during World War II. And much around the world, what is used when you have to make a weld and you need to decide what to do or whether what you did is good or bad, is based on the documents that the American Welding Society has compiled. Places like Canada, we have our own standards. And guess what? You just change the sticker that says AWS and you call it Canadian Welding Bureau, and it's more or less the same. Places like China, you use no, don't go. Places like China, they use the American standards outright. Places like Argentina just use the American standards outright. So it's awesome that he's coming. As I'm waiting for this to turn on, his name is Tom Leinert, and he's been a researcher for a long time, and he worked at Los Alamos National Lab. Anybody knows what that is? If I say Project Manhattan means anything to any of you? Okay, that's the original site of the Manhattan Project. Oh, here he's walking in, so that's good. So nobody upset him because he's been dealing with dangerous stuff. Hey Tom, welcome. Come on in. So everybody, this is Dr. Tom Leinert, current president of the American Welding Society. And I think you met Ale, our PhD student, last class.
Will this be on the quiz?
Yeah? Well, that's what they would wish is on the quiz, right? These are the easy questions. So the projector should start now. So what we saw last class was we discussed welding engineering. Does it matter or no? What the hell it is? I think I tried to make my case that welding is so much more than the act of putting down metal on a plate. And welding engineering is not a welder, is something in particular in which is very important, although we are not always aware of that. And that will be the focus of this class. So as soon as the projector starts projecting, what I want to move on is to the next topic on this class, that is the concept of joining. So in this class, we're going to be talking a lot about welding and subtleties about voltage and subtleties about current and heat input and bainite and all those things that you might or might not know what those are right now, but doesn't matter because you will later. But all those details, and if you go anywhere here and you talk about welding, people seem to know so much about welding and their 6010 electrode and all that stuff. But welding, in particular the type of welding we use so much here, is a tiny, tiny, tiny way of the many, many, many ways of putting two things together. So before we get into the details about welding itself, let's put welding in context of all the ways of putting two things together. So that's called joining, right? That includes welding, and includes stapling, and includes gluing, and all the things you did in kindergarten and beyond. So let's start here. There you go. The definition of joining that I like the most is actually the motto of the Welding Institute in England, in Cambridge, UK. There is a very, very large welding research and consulting institution, very famous, right? And it's a duobus unum, right? You might know in the US they have the a pluribus unum, which means from many states to make this one country, right? A duobus unum means from two to make one. That is the definition of joining. You have two plates of steel, now you have one. You have the two pieces of tube, and you weld them and you make a chair. From two you make one. And so typically the joint affects only a small fraction of these parts, right? And we're going to see why this is important, right? Is when you join, you don't destroy everything, but something you have to affect so it stays together. Articulated joints, like your shoulder joint, that's a joint. That is outside of what typically is called joining, although I'm going to discuss them soon. The ideal joint, at least what my advisor taught me, is the no joint. If you could make a ship in one piece, you would be awesome, right? In a few cases, you do the joining as a way of improving your process. Typically, a joining is something you have to put up with, and you wouldn't do it if you didn't have to. So very often, we would say how good our joint is compared with if we didn't join it, right? How much worse are we than if we didn't join it? Now, a joint has many, many properties. And again, the topic of today is to be aware that what we take as our whole life, right, is a small part of a much larger reality. In welding, you live and die by mechanical properties, such as strength, toughness, hardness, right? In the case of articulated joints, like would be the mobility, right? You live and die by those. And people make lots of money, or lose lots of money, or lose life based on this. But these are not the only properties. For example, you have electrical properties too. If you're welding something that is going to carry current, right, you better not have whole lots of losses. For example, if you're working with nanotechnology and you have two nanowires and you put them together, the fact that they are touching means they're joined somehow. And in this joint, sometimes you have what is called an ohmic joint, in which current can go both ways and you have some sort of a resistance. Or sometimes this can be what is called a Schottky joint and acts as a diode, as something that is a current goes in one way but not in the other. You're affecting the electrical properties. We seldom care about those, but they exist, and some people do. And I want to bring to your awareness that when you get a job and you live and die by toughness and hardness, that is actually one of the many things that could be. It just happens to be the one that matters a lot to us and many. Magnetic properties. As those, funny enough, those matter to us. Some material is magnetic, like normal steel, like the one in the chairs. Some material is non-magnetic, like some stainless steel. Some material, like the stainless steel, depending what you do to it, it can go from non-magnetic to magnetic. Who cares? Well, you care. And the reason is that when you're exploiting, you're drilling for oil, for example, in SAGD, those type of things, those of you who know about oil and gas, right? You have to go 2 pieces of pipe. You have to go about 1 kilometer or more underground, separated by a couple meters, right? Have you ever thought how you do that? How do you make something 1 kilometer away, 1 meter away from something else, 1 kilometer away, and you don't see it, and you don't touch it? How do you do it? So they use a system of magnetic orientation, right? A kind of a GPS based on magnetism. Now, if these parts, when you make them or when you repair them, they become magnetic, Now, instead of sensing all these very weak magnetic fields that give an orientation, would be confusing with itself, right? Very important not to lose this magnetism, not to gain this magnetism. So for us in this province, magnetic properties matter a lot, right? Who knew, right? For most other people, they don't matter, but for us, they do. Optical properties. Now, for example, if you have a laser like we have in the lab, you have an optic fiber, right? And this optic fiber is separate from the rest of the laser. The light must go from one light path to the fiber laser. There's a joint there. And the joint has to be good enough, should not be opaque, right? Should not be reflective, and many more things. Now, I don't care very much about those because I'm a mere user of it. The guys making lasers or the guys making photonics, they care a lot, right? So we're going to talk so much about toughness and hardness. You might forget I ever said this, but I know it's going to be in the back of your mind saying, you know what, there's so much more just to this, and that matters. So there are many ways of classifying the welding processes or the joining processes. And if you get books, everybody has a different spin. And I didn't want to be any less, so this is my spin, right? And the truth is I would love to do something that is kind of a mathematical taxonomy, something in which everything, it covers everything with zero overlap. I haven't been able to do it, but this is the best I could do. So everything that is joining, that means of two parts to make one, I would divide it in two parts. One is continuous and one is discontinuous. I'll tell you what those are in the next slide. The continuous I'm going to divide into diffusion and flow, and this into solid and liquid. Right now you see you just see a bracket there. It doesn't mean much to you. In about 45 minutes, that's going to be make a lot of sense to you. So let me walk through each of these little parts as an introduction of these. In the end, all our class, or almost all of our class, will be on this little part of this tree, right? And isn't that amazing? We're going to learn so much. You're going to have like a really big exams. People make money. People make lives. Well, not make life, but lose lives. All living in here. But all these other things exist, right? And matter. And very often, if you ask anybody in the province how you do this or that, they would say 60-10 electrode. But they say that because they don't know any of these. Maybe the answer was 60-10 electrode. Maybe the answer wasn't. For you, you'll say maybe 60-10 electrode or maybe any of these other things. And you'll think. And that's what's going to make a difference. That's what's going to save us. All right, there you go. Let's start with discontinuous joints. What do I mean by that? By discontinuous joints, I mean that they are touching mechanically. The atoms are not bonded, right? So in this mechanical way, right? This is the mechie type of joining. This is bolt and nuts, right? This is rivets. You need a nonlinearity. That's essential. So a nonlinearity can be friction. A nonlinearity can be plastic deformation. A nonlinearity can be a second-order deformation. It can be contact. And you might or might not have a supplemental part. For example, if you have two pieces of paper and you staple them, you have joined them, and you have a supplemental part that is a staple, right? So by going through this classification, there is also something interesting, that if we make some sort of a taxonomy that is systematic, you might, if you're lucky enough, smart enough, given enough of a chance, by going through this systematic procedure, you might be able to invent or rediscover the joining process that you need, right? The joining technology you need, instead of just reciting what somebody else said or accepting what somebody else does. So friction, for example, a nail. Have you ever thought like what holds two pieces of wood in your deck in your backyard is friction? If the nail was all like perfectly oiled up, it's good for nothing. Same with the screws. right? You screw something. Have you ever thought, if it wasn't for friction, you cannot get two things together, right? Nuts and bolts, self-tapping screws. I mentioned this other nonlinearity, plastic deformation. For example, here you have a folded joint, right? So chances are that everybody here likes either beer or soda or both, right? When you get a can, right? That can has a body and has a lid. If they're together, they're joined. How are they joined? Well, they are actually joined with this folded type of joint, and that involves plastic deformation. If you don't deform plastically, it's going to come out, right? Rivets, plastic deformation. You can have a pop rivet with the machine, or you could do like super old school, the rivets that were red hot and you were hammering on. But in the end, the reason a rivet is keeping two things together is because you deformed it plastically. Same with a staple. You have an additional part in these cases. In this case, you don't have an additional part, but in this case, you do, right, for joining. Second order deformation. That doesn't sound like a cool buzzword here. Second order. It's not first order deformation. It's second order deformation. So what is this, right? First order deformation is a deformation that is so small that if it goes left or goes right, it's essentially more or less the same as not having gone anywhere. But second order deformation is something that moves enough such that moving a little bit to the left or to the right is not the same. For example, if any of you ever tried to open like electronics, about 10-year-old or 20-year-old electronics, now they are all glued, the electronics. If you open a phone, it's glued. But before, they had this type of snap joints, right? So the snap joints are the ones that you put them together and you hear snap, right? And so they can be irreversible when they are like a hook, right? Why is it second order? Because it came, when you press it, it came in and it deformed a bit. And when it wants to go out, it's not the same, right? It's locked. So it can be reversible if it is a hook, it can be reversible if it is kind of this button, right? An example of this, those of you who have, I don't have any of those now, like these snap-on buttons, right? That is second order deformation, right? But not plastic deformation, right? Otherwise you could do it only once, right? These things. Another nonlinearity is contact. What is nonlinear about contact? Well, again, as I said, when left and right are not quite the same, or up and down is not the same. Here's my cell phone. I put it on the table. That's contact. It can go up, but if I want it to go down, I'm going to destroy my phone, right? So I'm not going to do it in front of you. But there is a nonlinearity. One way, yes. The other way, no. Contact. And that's the basis of all woodworking. That's the basis of the temples in China, in Japan, and the rest of Asia that are done without nails and without screws, right? And without glue. That's joining. That's contact, right? And in the case of those temples, gravity matters. In the case of woodworking, you do it in such a way in which the things are together, right? And typically you would put glue, but you don't put glue so it holds the joint. You put glue so you don't lose the contact, right? Because, for example, if this dovetail moved to the side, would snap out, right? So you put glue so it doesn't move to the side. And then all these are like things I wanted to bring to you as an example of joint methods. For example, this mortise and tenon, right? That's the way they used to make old ships, right? They would make the planks of wood, carve kind of a hole, put this like a tenon, and put a lock, right? That was in Europe. The Vikings did it in a different way. So this is very interesting. All these are like Meki type of joints, right? It's mechanical, nothing chemical, nothing too interesting for us. Before we move into what is interesting, what type of joint is this? Say?
It's a seam.
That's a seam. That's good. And now this type of joint would be continuous or discontinuous? Yeah, I didn't teach you anything else. So good choice. And of course, this is continuous. There is nothing chemical in the, you know, this is a gene, right? Like a stitching of a gene. So what is the nonlinearity that we have here? What is the nonlinearity? Say? Friction. Do we have a supplemental part? Yeah, that's a thread, right? That's a supplemental part. Would be much like putting a staple, but in that case, the nonlinearity would be plasticity, right? But the beauty of this then is like it's easy to put in and out. Remember last class I told you how knowing how to weld was so important to the Germans or to the Russians, and not doing the welds right was so bad in so many cases? One of the keys in the development of humanity was joining, because putting the pieces of fur together to make clothing required joining, stitching. That's a huge invention. The reason we're not hairy like monkeys is because we could like steal somebody else's hair, right? That's the only thing that helped us survive through the cold and all those things. And that all comes to joining. But that's the joining of the Mechie, so let's forget that. I'm a Mechie, but I betrayed my roots, I guess. There you go. This continuous friction supplemental part. Super important. Who knew, right? No joining, no humanity. And the monkeys would get to keep their fur, right? And whatever, the bisons. So let's talk about continuous joints. Those are the ones we care about, but this is still way beyond welding, because the key concept here is that now the atoms share their orbitals. And it can share the orbitals at many levels. This sharing of the orbitals is called rapprochement. I don't know who came up with that word. Again, another cool word to drop at a party. So this Friday, you guys are ready. So this bonding can be chemical, in which things are really together, or can be kind of more subtle, like van der Waals forces. You might have heard of van der Waals forces, right? Those are not a chemical joint, but the polarity of the molecules and whatnot makes things together. For example, the screen protectors on the cell phones, they have no glue, but they're stuck there. How? Van der Waals forces, right? So there are two key questions, and when we classify this classification I made of joining processes, one is how did the atoms get to rapprochement? How? And the second question is, all right, and where do they come from? With those two questions are going to give us a sense of like pretty much everything that means putting two things together in the form of continuous joints. Like anything else that involves chemistry, right, or like some sort of atomic thing, the key concepts here are pressure and temperature, right? Or pressure, let's call it stress. Let's get the first. Diffusion bonding, right? People make a living out of this, right? We do close to none of this here in the province. But in diffusion welding, which is called welding, but welding has a proper definition, and this doesn't meet the definition of welding, but people still call it diffusion welding. So in diffusion welding, you don't melt things. It's super gentle. And also, you don't put too much stress. It's super gentle. This is like, I'm going to put the two of you together there. I hope you join. And they join. It's crazy, right? You make planes with this. You make crazy stuff with it, right? And so what happens in this case, the question I said is, how do the atoms come together? And they come together by diffusion. So the atoms are meandering like through the atomic lattice, and they come to the joint, and they like the joint, and they stay there. And eventually, a joint that started like this is the one metal, this is other piece of metal. These are the grains, right? The crystalline grains. I believe all of you took some MATI class, at least MATI 202, right? All of you? Not civil engineering? But you know about grains and that in the metal, right? Okay. So these are the grains. And because things are not flat, no matter what people tell you, they are not flat. When they touch, they will touch at the asperities, right? So in reality, when you think I'm putting so much pressure, it's not true. You think you're putting so much pressure, but in reality, there is a lot of pressure on these asperities that are a small fraction of the surface, right? And then for those things of thermodynamics, right? Diffusion makes the atoms come here and be happier, and they start to essentially erase this interface. And at the end of this diffusion process, you'll end up with something that doesn't have a trace of the interface in the best of all cases. Diffusion bonding is the closest you get to the no joint, right? What is the best joint? The no joint. All right, this is the closest you get. Look at this micrograph here. The arrows indicate where the original interface was. But if we didn't put the arrows, you don't stand much of a chance of knowing where it was. This is a good one. Now, sometimes you have little pores. If the surface was not perfectly cleaned, that will act as a barrier, so that would be a problem too. This is good, but now there's something interesting. Diffusion bonding that requires these clean surfaces is especially good for titanium. And the reason is titanium, unlike aluminum or unlike stainless steel, titanium, when it gets a little bit of oxygen, it sucks it in instead of having it in the surface. So the surface of titanium, if you do things right, is typically clean, right? Surface of aluminum is not clean, don't matter what you do. So you very seldom are going to see diffusion bonding of aluminum, but very commonly you're going to see diffusion bonding of titanium. Now, for those things of God, it just happens that titanium also has superplastic forming ability, which means you can stretch titanium the way you would stretch like pizza cheese, right? Like you stretch and stretch it forever. So if you combine this ability of having a clean surface with this ability of doing superplastic forming, plus the properties of titanium of being strong as steel, but at half the weight, so that means you can do interesting things for things like airplanes, right? And you can make structures like this in which you put the two pieces here. You put the two pieces of titanium together with something that separates them. You heat it up, you blow gas in there, an inert gas. You don't want to be blowing anything with oxygen. And if it is hot, it's going to start with superplastic flow. And eventually, you're going to make a 3D structure that is very stiff, that is very light, and was relatively cheap to make, right? Because of superplastic forming and because of this property of titanium. You see this front fan of a passenger plane, right? Now it's not so much true, but in the past, Rolls-Royce used to make those front fans out of titanium, while GE was making them out of carbon fiber. And it was very interesting. And the reason is that the guys in the UK at Rolls-Royce developed the technology for superplastic forming and diffusion bonding of the front blades of the front fan of passenger engines, right? And it worked very well. So the older Rolls-Royce engines are made out of titanium, while GE was making them out of carbon fiber. Now Rolls-Royce is also moving into carbon fiber. But this is very interesting, very different approaches. And the whole approach of Rolls-Royce, which I'm not talking about a little company, was based on this diffusion bonding. All right. You see, this, we don't do this in the province, but it means so much. And now you're being exposed to it. You can think beyond what most people would do. So how do the atoms come in? I said diffusion bonding, you just let them be, and good things happen. But maybe you want to be a little bit more intense than that, and we have those that are called solid state processes. In this case, the atoms come together because you're smashing them with a hammer, for example. You're putting so much pressure, so much deformation. The atoms come together because you're forcing them by force, right, to come together. So often the role of temperature is to soften the material. The temperature can come from external heat sources, like you heat it up. Like, for example, forge welding, right? Caroline, you worked at EVRAS, right? And you work on ERW, right?
A little bit, yeah.
Yeah, and in ERW, electrical heating heats up the joint that then gets essentially is a solid state joint, which you have in the end, right? There's a process called spinduction that was developed in this province in Calgary, and it's very, very promising in solid state. In these cases, you have external heat. Now, there are other processes in which the heat comes from the internal heating from the formation, right? If you get a paper clip and you bend it enough times, it breaks. But if you have done the experiment, you also realize it gets really hot at the bending point, right? That heat, where does it come from? It comes from all this force and this displacement you make. This mechanical energy you put in is transformed in thermal energy. So there are processes like friction stir welding, which you're going to see in our lab in action, in which you don't put any external source of heat, but the thing gets hotter, right? And it's because you're mechanically deforming it. All these acronyms, and I'm aware, mean nothing to you right now, right? It might seem impossible to remember them. But I wanted to bring this up just to introduce you. But we're going to, each of these processes, we're going to study in detail. And you're going to know lots about them very soon. But right now, just please keep in mind that there are many ways of doing things, getting the atoms together in many ways. There are two that I would like to highlight. One is called friction welding. Friction welding, typically you do it in cylinders or bars. You rotate one against the other, and of course, because they rub one against the other, it gets hot. And if it gets hot enough, it's going to get soft, and then you press it, and voila, you have a joint. That's the way you make the shaft of jet engines, right? You can do it rubbing like this linearly. Funny enough, this is a technology that is coming to this province. We didn't do any friction welding in this province, or not any meaningful amount, until recently. But that might be something we do a lot, because it's a good way of putting very brittle wear protection layers on top of tough steel, right? So these type of processes, you don't put heat from outside, but it's the friction that brings the heat, softens, and force brings the rapprochement. This thing here that looks like the waves of the sea, that's called explosion welding. And guess what? It's because you're exploding something. That was discovered after World War I, in which sometimes they would see shrapnel or the head of the cannons, right? Cannonballs, like stuck to the metal. And people said, why is it stuck? And what they saw is that when two things hit each other in the right conditions, you can have supersonic waves inside, and they can create localized pressure and very high localized deformation. With explosive welding, the interesting thing is you see this is one piece of metal. This is a cross-section of a weld, and this is one piece of metal, this is the other. There might or might not be rapprochement there. It's very close to each other, but there is mechanical interlocking, right? And for that reason, you can make things that are very dissimilar, right? And they will stick together. We care about this because this is a technology you use to make layered plates for chemical reactors in which you want to have steel on one side and titanium on the other side, right? You cannot do that with fusion welding because you'd have a lot of other problems. But explosive welding can do those. Very few places can do explosive welding. You can imagine, it's not that in our lab downstairs where you guys are going to do your hands-on, It's not that we can detonate an explosive charge and get away with it, right? It's very, very few places where you can do it. So what are we talking about? Joining. Joining is putting two things together. If the atoms don't connect with each other, mechanical, makey things, I just wanted to expose you to that. And I mentioned many times. Good. Then I said, okay, now the atoms are together. How do they come together? Well, because we hit them with everything we had, right? That's the solid state process. The other one was like you let them gently get together with diffusion. Okay, let's say we don't want to hammer them to death. There's another alternative. Let's put a liquid, right? The liquid will cover all the gaps, right? And this liquid would maintain the two things together. So these liquid processes, I'm going to divide it in two types. One type is when the liquid comes from outside. It's external liquid. For example, glue. Piece of paper, glue, put them together, and they are together right? That is an external liquid. That's the case of glue, but it's also the case of other much stronger processes like soldering and brazing. When you see the plumber, like with the pipes and this little torch they have, right? They're doing brazing or soldering, right? Depending on what type of material they use. It's more or less the same thing. So instead of using glue, what they do is melt a metal that goes in. But this metal is not a very high temperature metal, right? It acts more like a glue. Any of you have worked with electronics, soldering electronics? Any of you? All right. You don't want to melt your circuits, right? But you do melt something. You melt this solder, right? So this is one of those type of processes in which the rapprochement happens because one of the elements is liquid and reacts and gets together with the other one. Brazing, soldering, there's something called weld brazing in which you're not actually welding the parts, but you're using a welding technique. So you melt the metal and it's going to have this glue type effect. The original interfaces remain, but I put it in quotation marks because really between the interface, in the case of brazing or soldering, in the interface between this liquid you put in the case of a metal, and the metal structure you want, for example, the copper pipe and the solder, right at that interface there is a chemical reaction. And what you would see, what the solder or anybody, the plumber would see with their eyes as one interface, in reality it might be many interfaces of different chemical reactions, right? So to some extent you can say the original interface remains. To some other extent you can say, well, it was turned into other interfaces due to the chemistry. So one good thing of this type of joining is that it has little effect on the components. For example, I put two pieces of paper and I glue them. The paper is fine. If I try to come with an acetylene torch with the two pieces of paper, it's not going to be fine, right? So when you have a plumber making your copper lines, right? If they don't like what he did, like it comes, heats it up, and separates it again. So this is a reversible type of joining. For the most part, everything I tell you in welding, there will be a counterexample, I promise you. So if you ever want to prove me wrong, don't waste your time. I know I'm wrong just to start. But most of the times I'm right. So I'm going to take that one. So when you do this type of joining, and we'll have a little section just specific on this. What do you think about cleanliness? Right, it is pretty important because if things are not clean, the liquid is not going to flow in, right? So what do you think about the size of this gap, right? It matters a lot because you have these capillary forces going in. I'm going to discuss this later, but there's a big paradox. When does it flow better? When this gap is big or small? All right, I don't need to teach anymore. That's exactly right. All my life I thought the bigger the gap, the better. But not true, because the capillary forces are higher with the smaller gaps, right? Assuming you have a wetting angle. But if the part is dirty, you might have a non-wetting angle, and then you're never going to get it in, right? So unless you make a huge gap. But if you make a huge gap, then it's not going to be a good joint. Typically, these type of joints are weaker at the interface than the base material, and they cannot resist much temperature. So typically, if I do soldering or brazing, I can go up to the temperature of the solder or the braze, but I cannot go to the temperature of the copper. The copper can take a lot of temperature. But if I go that high, I'm going to remelt my solder or my braze, and things are going to come apart. So those are pros and cons. There are ways around it. There are ways around it. For example, in a turbo in a car, typically you have a metallic shaft, and the turbo is made out of ceramic. The only way of putting those things together is with brazing, right? But then you have this high temperature metal, this high temperature ceramic, and you put a brazing, and you're ruining all these high temperature properties, right? That's a problem. There are ways around it. It's called transient liquid phase bonding. Don't worry, it's not in the exam. But right? But this is one of the drawbacks of this approach, right? All right. We're walking slowly into welding, little by little, right? So when I said, how do we get rapprochement? One is diffusion, one is like beat them to death, the other is just make it liquid, because the liquid will go and get the atoms in contact. Okay, fine. And then we said, okay, the liquid can be external, whether it's glue or brazing. Now, many people would kill me, say, how can you say brazing and gluing in the same line? Yeah, I'm saying it. And the president of the American Welding Society is not going to hold it against me. Right? So, but then the question, I said the second question is, where do the atoms come from? So the glue comes from my glue thingy, right? But how about if I melt my same material so I get my atoms from the same base material, right? That's what is called fusion welding. That's normal welding, right? Like you melt the metal, right? And now the metal that bridges this gap is its same material, right? And you see those acronyms? They don't mean anything to you. And you probably are terrified that you need to memorize them. And you guess what? You'll be talking about that the way you talk in English or anything else, because these terms will speak to you. You'll know exactly what those are. You'll be able to do calculations on those. Right now it sounds like whatever. Soon enough you'll be saying, oh, well, let me tell you why GMAW is not the same of GTA. I have so many things to say. So right now, just take it. All that matters here is you can get rapprochement in liquid state, and in cases like the metals, you can melt the base metal. You cannot do this with paper. And if you do, let me know, because we file a patent and we're going to be millionaires. But when we do this base metal melting, there are still more divisions, and there are more things into which things are narrow and narrow and narrow. So you can have no filler, right? That is what is called autogenous welding, right? So I have two pieces of steel put together all too well, but they are separate. I come with my welding machine. I melt that interface, and when it goes solid, it's one, right? Awesome. That is called autogenous. And there are good reasons to do that, right? Now, you can have joints that have a filler. That is what we do in this province typically. You cut a groove between the two plates, for example, and you fill this groove with your filler, with the electrode, right? Of course, you have to melt a little bit of the base material so it's all together, right? Now, when this filler material is more or less the same as the base material, it's never exactly the same. So let's not get caught in mathematical subtleties. But when it's more or less the same as the base material, we're going to call it homogeneous welding, or homogeneous. Any natives, how do you say it? Homogeneous or homogeneous? Oh, God. Okay, it's both. You have a take?
It's wherever you're from.
Homogeneo.
If you're from Ontario, you'll probably say heterogeneous. If you're from over here, probably you say homogeneous, but you would probably say homogeneous.
Okay, we're in Alberta. We're not going to speak like in Ontario. You got that? Okay, we have the camera. So homogeneous, right? Like we got it. So we call it homogeneous. But then the filler metal might be super different. That you called, what do you call it then? Heterogeneous? Or heterogeneous?
I think it's heterogeneous.
Heterogeneous, okay, so I have a problem now. Okay, maybe I'll speak like Ontarians. But we do this in the province. For example, you have a steel plate, and you want to make a wear-resistant coating. And the wear-resistant coating is typically nickel-based, but your steel had close to no nickel. But the coating is pretty much all nickel, right? This is heterogeneous. You want to weld cast iron. Cast iron has close to no nickel. But the electrode you're going to use, lots of nickel, right? Good reasons to do it. And we're starting to think, right? Like we're starting to see all these possibilities. What we do in this province, 99%, this type of thing in steel. Now let me tell you what. If you learn what we do in the province, it's good for you today. But it's a dead end, because what we do in the province today is not cost effective competing in a global market. So one of the reasons industry wanted to have this welding program and we're teaching this class is because we don't know exactly what to do, but we know we need to do something that is different than what we have done before. So the reason I'm teaching you all this, including how to make like wooden crates, right, is so your mind is open to all these things. And you might not choose all of them, but you're able to choose some of them, right? Instead of being stuck on, we have always done the same way. So now we go back to our brackets. It makes more sense to you, right? Joining can be continuous or discontinuous. You know what that is. The continuous can be based on diffusion or based on some flow. The flow can come from beating the solid so it flows in plasticity, or can come from liquid, having melted the metal, and it flows. If it is liquid, it can be without fusion of the base material, the case of glue and paper, or can come with fusion of the base plate. Fusion means like melting it, right? And that's the typical case of fusion welding. Now, if you do fusion welding, it can still be you don't add anything or you add something. And if you add something, can be more or less the same or can be not the same. So many things, right? And you're going to see that even between this, from here we get to stick welding, and stick welding you get to 60-10 and 70-18, and that's all the province knows, right? Like this sub category. All right, look. So I mentioned pressure and temperature before. So what would be the role of temperature in this? Things that you can already think intuitively. In the case of solid state deformation, right? Temperature helps you many things. The temperature will take out adsorbed gases, right? Like moisture, organic contaminants. Something funny about welding. If you want to put two pieces of steel together, you imagine, yeah, if they're clean enough, they're going to come together somehow. But cleaning costs money, costs time. So the real deal of welding and joining is not putting two things together the way they should be. Is putting things together the way they are. They're rusty, they have oil, they have all kind of weird stuff, right? So the challenge is not so much doing it, but doing it in a production environment with the real economic constraints. So things like adsorbed gases, and moisture, organic contaminants, oil, right? Temperature also would crack oxides because it has different thermal expansion. Temperature can either decompose or dissolve oxides, right? So it's good in many aspects. If you do it wrong, the temperature can end up oxidizing things too if you don't have an atmosphere protection from atmosphere. Also, temperature lowers the flow stress. By flow stress, I mean when you're deforming things plastically, they oppose your deformation, right? But the hotter it is, the less they oppose you, right? It also, temperature promotes recrystallization. So I mentioned that the metals, when we talk about metals, with ceramics too, but in metals, you have a crystal structure, right? When you do things to it, that crystal structure is still there. If I'm putting two things together, I'm going to see this interface because the crystal structure is still showing it. But if I have recrystallization, that has more chances of erasing itself. Right? It's a relatively advanced metallurgical concept, but it's one that helps you very much. Now, obviously, the role of temperature in fusion in these processes involving liquid is temperature is what gives us melting, right? At the atomic scale motion, like the diffusion thing, diffusion is faster, but a lot faster as we increase temperature, right? So if I have a diffusion joining process that takes so long to happen, if I increase the temperature, typically it's going to happen so much faster, right? But there is a limit. You cannot be so happy that you end up creating other metallurgical problems like phase transformations, including incipient melting. That was temperature. How about pressure? Pressure for those processes in which we have macroscopic motion, like solid state processes, right? The pressure disrupts all these contaminants we discussed before, before they could be degraded or evaporated. Now, pressure or stress. What does it mean? Well, I'm just taking them out by brute force. And pressure also increases the area of real contact. Remember, you think you're putting two things together, but in reality, you're only putting the tips of the asperities together. But with more pressure, these asperities get flattened and you have more area. When you have liquid processes that involve liquid, right, typically having pressure is the melting of the substrate, right? Typically, you don't want to put pressure. For example, you're welding and you're melting this. You don't want to start pressing it together because it's going to deform really badly. There is an exception to this. In resistance spot welding, that is the way you make cars. You put pressure, right? And if you ever saw a video, which you will see when we teach that, of resistance spot welding, you see sparks flying. In reality, those are not real sparks. What is going on is that you melt it, you put pressure, you're squeezing out molten metal. And that's what you see flying, right? But typically, if you're going to have melting of the substrate, you don't want pressure. And if you don't melt the substrate, that is the case of brazing, for example, pressure is important because it helps you keep a tight gap. Nothing is flat. This is another interesting thing of welding. If anybody asks you, what is this plate? They say, oh, this thick or this wide, this long. Yeah, but nobody's telling you that really the plate is not flat, and the non-flatness is very complex, right? So when you do brazing, in which you want to put two things together, and they need to be tiny fractions of a millimeter together, the best you can do, put pressure, because this pressure is going to take all this deformation and get it as close as you can. But now you know that if you have a plate that is not very flat, brazing is going to suck. It's going to be horrible, very difficult, right? And zero pressure is never too good for brazing, right? Too much pressure might not be good either, right? Because you don't want to start having contact in the asperities. So, and the atomic scale motion in diffusion, right? Typically, at the beginning, you want to put pressure, so you have these asperities in contact. But the funny thing about diffusion is when it started to go, you let go of the pressure, and the thing sucks into itself, by itself. Very interesting, right? So, if we put these two concepts together, I made this graph. I like it, actually. It's not in any book. The book is in writing someday. It's going to come out. In the horizontal axis, we have what is called homologous temperature. Any of you know what homologous temperature is? Okay, so let's get the temperature at which something is happening, right? In Kelvin. And then I'm going to get the melting temperature of that material in Kelvin. So I'm going to do real temperature divided melting temperature in Kelvin. If the number is 1, what is the temperature of that material? Melting. It's melting, right? Number is less than 1, what do I have? Solid, right? More than 1, liquid, right? So I'm saying here, the 1 is temperature of the joining compared with what is the lowest melting temperature, the base material, the filler metal, or whatever. Less than 1 means nothing is liquid, right? So from here to the left, we have all this non-fusion welding, right? These solid state processes. From here to here, we have the processes that involve liquid. This is the horizontal axis. The vertical axis is macroscopic pressure. So macroscopic pressure means my force divided by the macroscopic area. I'm not talking about the asperities here. So I'm dividing the real pressure, right, by the flow stress, right? I mentioned to you, as things are deforming plastically, right? They resist motion. The concept of flow stress is somewhat similar to the concept of yield stress you might be more familiar with, right? So if this is 1, it means I'm deforming plastically. If it is less than 1, I'm not deforming plastically. Being more than 1 would be pretty tricky, because how do I put more force into a metal than the force it can take, right? Okay, that said, this 1 point matters. So let's think. Diffusion, that means we have a low homologous temperature. Nothing is melting. Remember? Nothing is melting in diffusion. Nothing should be melting. And the pressure should not be too high either, right? The pressure is not too low either, because we want to have at the beginning a good contact. I put diffusion here. Let's talk about fusion welding. Has to be more than 1 here, because something has to be liquid. But no pressure, right? Unless it's resistance spot welding. Because if I do that, I'm going to squeeze out all the molten metal. Brazing and soldering. I do have something liquid, right? I have my braze and my solder. But you need a little bit of pressure just to keep the parts together as the process is happening. Let's go back here. We can have solid state processes, right? And people, and this is, I'm kind of waving my hands, but remember when I talked about recrystallization, how these grains of the metal turn into something new, right? Would be like the crystalline structure of a material is like the streets in a city, right? And the grain boundary is like a neighborhood. And recrystallization is like rezoning, right? Like all of a sudden, you still have streets and avenues, but you decided that the limits are going to be different, right? When it's cold, this rezoning, this recrystallization is very difficult. And for that reason, when you're just smashing something to be together and you didn't give temperatures to do the rezoning, it's full of residual stresses and dislocations and all those things that is going to make it very, very tight and have some properties that can be good or not. But if the temperature is higher, right, now you give a chance for all this stored energy in your neighborhood, right, in this crystalline structure, to release and turn into a new grain that would not have those that stress. Typically would be softer, right? There are advantages and disadvantages. You have both, right? I put explosive welding up there, and it's funny. You're going to ask me, how can you have more force that the material can take? How can it be? I meant it. We can argue if it is right or wrong, but I have a point. How can you have more force than the material can take? So if I put force on something that can take little force, I'm going to start pushing it, right? Force, or delta F, is mass times acceleration. And that's what happens in explosive welding. You have these shock waves that are essential to the process. And that's why you get to see all these deformations that turn into mechanical interlocking. So this explosion, right, actually causes local force imbalance that creates shock waves. So this is very uncommon. Typically, when you have plastic deformation processes, you're right there at 1, right? So if you see this graph, now you can start thinking of other joining processes you would like to invent, or you have seen but we haven't discussed. They will likely fall somewhere in here. And you'll know also something else. If I don't put pressure and I don't put temperature, nothing happens. That's what the mechis do, right? Or the civil guys who bolt the structures, very bad. Not to mention concrete. So now, if you put pressure and you put temperature, you're trying too hard, right? I mean, you're going to destroy the thing. So actual joining lives somewhere in here. The joining we're going to discuss in class is almost all this one here. But it's a whole world out there, a whole world that might be the world that saves us. So how are we doing so far? Do you guys have any question about this joining? OK. I think this is pretty cool because it's going to help you see things with different eyes, more than the eyes of, I know so many welding tricks, of the eyes of, all right, I need to put this building or this ship or this airplane or this oil sands truck together. What would be the best way to do it? I have a problem. What's the best way to solve it? Something broke. Why did it break? Is just a material low quality, or am I doing the wrong joining process? Should I bolt it? Should I weld it? Should I braze it? Should I glue it? All of those are open. Ships are welded today. But when you repair ships, I know this at least of in the Greek Navy, because my first student was in the Greek Navy. The way you fix cracks in the Greek Navy ships is you put like I don't remember if it was carbon fiber or glass fiber, and you glue it with epoxy. Aha! But when we have cracks in our oil sands trucks, we try to weld them. Now it's pretty funny because you have a crack, so you weld it, and now you have 2 cracks parallel around the weld, and then you go on a 2 to the end problem. So that's why we have this class. So I want to tell you something that I learned from my advisor, and it's in the books because he wrote it. So in all this whole thing I told you, right, fusion welding was this tiny thing. Right? Fusion welding is this. Now, fusion welding can in itself be classified into many, many things that are so different to each other that some people live in little boxes without ever knowing that there exists other box, or if they know it exists, never talking to people outside. Isn't that funny, right? And one good way, and I think this is super smart, one good way of classifying these boxes within fusion welding is by the intensity of the by the intensity of the heat source, right? How do we create this local heating, right? So let me tell you something interesting. Tom, it means a lot to me that you're here. So when I became a professor in Colorado School of Mines in the US, I had to write a very, very important proposal. And I wanted to work on welding. But in the US, it's not like here. The welding is not so cool. So I had to write this proposal. I wanted to write this proposal in welding. But Tom, you said, that's good. Just don't call it welding. Call it non-equilibrium processing, materials processing. And I got the money, and it was awesome. The funny thing, I did it because I had to do it, but this is so true. Why is non-equilibrium processing? Equilibrium means everything is the same, because if it is not the same, if it is hotter here than here, the heat is going to go. If you have more force here than here, it's going to move, right? Equilibrium means it will not move. It will not change temperature. But guess what? Welding is essential. The essential characteristic of welding is this non-equilibrium. For example, fusion welding, I'm melting something, but I'm not melting everything, right? I can melt everything, but I call it casting. That's another manufacturing process. Very good. but it's not welding and has very different properties. Okay, but I need to melt something, because if I don't melt or I don't put temperature somewhere so it happens, nothing's going to happen, right? When I said nothing happens, no pressure, no temperature. So this is amazing thing of welding. You have to make things happen locally, but not in the whole part. And it means so much, because when you're joining two parts, you have to put money and effort into making this part, money and effort into making this part. Now you're joining it. You screw up your joint, and you lost not only your work, but the work of this guy who did this, and the work of that guy who did that. Huge responsibility, right? And you do it by affecting some parts and not the other parts. And the most amazing thing of welding is that what gives you the right amount of heat with the surface tension of steel, with a bunch of things that didn't need to be, but God made them that way, that you can weld. If surface tension of the steel was different, or thermal conductivity of the steel was different, people would have never discovered welding. Welding was discovered, it was not invented. People saw an electric arc, oh, look at this heat, like, let's try this here. Oh, look, I'm melting. Oh, I can put two things together. The Wright brothers made their own welding machine, right? It's not that they were welding pipelines, but they could put two things together. But nobody understood why. And it's a miracle that just the amount of heat that comes from this big spark and the velocity at which your hand moves and the surface tension of the steel put it all together. It didn't need to be, but it was. And it's a huge change of technology, right? This timing has to be hot for so long, but not much longer because you melt everything, and not much shorter because you don't melt anything else. It's so carefully synchronized with other things, but we never synchronize it. It just happened. It's amazing. So energy sources. So they determine some fundamental aspects. Nobody would disagree with me that laser welding, whatever it is, but I said laser, is very different than oxyflame welding, because I said flame, right? You can imagine a welder is more expensive than having my flame torch, right? So that is very important. And we can classify welding processes. Many people do it by the source of energy. It can be mechanical, as we discussed, can be by plastic deformation, like friction stir welding, right? Is the source of energy is generated internally by friction. Can be chemical. If it is chemical, would come from a combustion, right? Like, for example, oxyfuel or acetylene, all those type of things. Explosion welding, right? It can be through a chemical reaction. For example, one way in which you would weld train tracks is called thermite. And it's a pretty crazy thing, which I'll show you. But you can have a chemical reaction that is so hot that melts the metal, right? But it's not a flame or anything like that. It's a local chemical reaction. The source of heat can be electrical, right? And this is what we use the most in the province. So the electricity can create an arc or a plasma, right? Remember last Tuesday I talked about these plasmas and the high temperature, right? That's arc welding of all flavors. And it could be by resistance, right? For example, resistance welding can be by induction, although few people do use induction as a heating for welding, right? Or it can be radiation. So that's an interesting thing. So radiation, for example, what is radiation? Light. What is light? A laser, super powerful. There are other ways of radiation. I'm going to include here electron beams, right? Although that is more mass than radiation, right? An electrical charge. But radiation can come also from a spatially broad source, like microwaves, right? Or electromagnetic or infrared. I uploaded 2 papers on this site because there is something super cool. What other sorts of radiation we have? Like solar radiation, right? And people tried this in the Soviet Union long ago, making parabolic mirrors. They did it. But the real funny thing that about 50 or 60 years after the Soviets did it, and of course it went nowhere, people in Spain did exactly the same without realizing. You have both papers, the old one and the modern one. But let me tell you something. If you need to weld something, solar energy, I'm not too sure is the best way. Not direct solar energy, at least. So you can make this graph that says the power density will determine, is related with the type of energy you have. And this power density gives you many things. So arc processes have this power density of about 10 to the 7, 10 to the 8 watts per meter square. Plasma, that is more or less the same, but with some constraints which we'll discuss next week, is a little higher energy density. Lasers or electron beams, those are called high power heat sources, right? High density heat sources. Higher. This is log scale. Huh? So each notch, it means 10 times bigger, 10 times more intense, 10 times more intense. What this graph also says is that if you have a heat source that is not intense enough, you don't melt anything, right? And it's true. And the reason fusion welding didn't exist until around 100 years ago was people had no way of getting straight thermal energy as concentrated as in an arc. But then with the discovery of electricity and people started to play and they figure out that, oh, look at this big spark, how hot it is. Then, without really knowing what they were doing, they started to move up here in power density. Now, here it says that there is no welding possible when you have too high heat intensity, right? Because if you have a too high heat intensity, what it says is you're not melting, you're just cutting, you're ablating it. There is some truth to that. But the funny thing is that it's not the whole truth, because in some conditions in which this is all done on the assumption that you put heat on the surface and the heat needs to travel under the surface. For the heat to travel under the surface, you need a gradient, right? So it says if you have too high energy density, too high intense of a heat source, the gradient is going to be so big that you ablate. Now, things like electron beam welding are like that for the most part. But if you're talking about microelectron beam welding, you have a penetration of the electrons that give you volumetric heating. And then you're not constrained by these gradients. And then all of a sudden, you can do what is considered impossible. So we had a guy who did a PhD, a master's on that, and got a big international award, the Grandjona Award. And I'm looking for partners to do the experiments. I sent this to John Elmer, but he couldn't do them because the conditions are very important. I sent them to Mike Rothmeyer in Germany, but their power supply was digital, so instead of being one big, very fast seam was stitches. I don't know, but I want to try it because all the theory indicates this is awesome, but until we do the experiment, we don't know if it is awesome. So look at this chart. I'm going to start telling you things which I put in this axis, the power density. And that corresponds to different things like fuel or flame joining to lasers, right? This is more and more and more and more as I move to the right, more and more concentrated heat sources. dW over W means depth over width. And if the heat source is very broad, is not intense, I have something that is very shallow and wide. But if the heat source is very intense, I can have something that is very deep and narrow. Very different thing. And you need to check? Okay, I'm about to finish anyway. I have 5. Efficiency, right? Melting efficiency means you wanted to have this joint, so you needed to melt so much metal. And you put so much heat. Do you put just the heat you needed to melt that metal, or you put a whole lot more heat? When you move very slowly, it's like having a bucket you're trying to fill with water and has huge holes. It's leaking all over the place, right? In this case, it's leaking heat. That's bad. It's bad energetically, but it's also bad. Guess what that heat does? it affects everything around, including creating distortions and residual stresses. Things like a laser, it's very efficient, very low distortions, very low residual stresses. HAZ, you're going to live and die by this. This is called the heat-affected zone, whatever it is, right? But it's the bad part of the weld, right? It's a part that the heat affected, and you cannot get away with it. In these not intense processes, it's very big because you were dwelling for too long in it, and the heat layer grew. But in things like a laser and electron beam, it's very small because you go very quick, right? Interaction time. The interaction time is very long. Interaction time means how long am I dwelling over a point as I do this. For example, in acetylene or oxyfuel, I'm like dwelling on it forever, right, until things get hot. But now if I have an electron beam or a laser, I'm spending very little time over a surface. I'm moving very fast. Same with the speed and same with the cost. I'm going to show you a couple of slides here. I'm going to skip this one. But concentrated heat, this is a cross-section of an electron beam. This is a cross-section of an arc welding, normal welding. And in this graph, we have how electron beam has very small distortion and how this normal arc welding has huge distortion, right? Because, of course, you have a smaller area that is affected. This is a super interesting one. The intensity of the heat source also tells you that in some cases you can only have an automated process. Things like a laser, if you spend too much time with the laser stopped, it's like when you're ironing your shirt. If you leave it for too long, you're going to burn your shirt. If you leave the laser for too long, you're going to drill instead of weld. So you have to move. But now, are you good enough to move that fast and still keep on the line? You're not. That's given by the interaction time. And you can calculate this interaction time, right? And this is the range. And this is a calculation of my advisor, Tom Eager, right, at MIT. And so he says, depending on the intensity of the process, and you know here we have like laser beam, and then we have like arc, and then we have flame, the interaction time gets shorter and shorter as the beam is more and more concentrated. Interaction time of humans is of the order of 0.3 seconds, right? This is the time it would take you to step on the brake of your car or to correct your torch as you're welding. And if you do that, right, you see where this interaction time humans have compared with the interaction time of the weld. You come to the conclusion that you can do flame welding, like chemical welding, acetylene welding by hand, no problem. You can do arc welding kind of okay. Plasma, very iffy, maybe, maybe not. Typically not, actually. Lasers, for sure not. Electron beams, for sure not, right? Because you just cannot do it. And this means, in some cases, will be a cheap process. In some other cases, will be an expensive process that needs a robot, right? So much to say. Cost. This is a super old graph, right? But it still is not that far off. You want to buy your flame torch, all right? It's going to cost about $1,000, true, of the order, $2,000, $3,000, whatever, $1,000, maybe a few hundred. You want a welding machine with an arc, $5,000, $10,000, depending how fancy you want it, true. Oh, you want a laser? Oh, well, let me tell you about that. Do you have $1 million here, right? Electron beam is even worse, right? So you start to see, oh, automation versus no automation, heat-affected zone versus not a heat-affected zone, money versus not money. And you start to see how decisions are made, right? And again, in the province, we do only this. Not true. We're doing quite a bit of laser now, right? We need to think about these things. So I'm going to stop here. And because it's being 3:20 is our time.